Welcome everyone to Algebra 2, Section 7.2, Simplifying Radical Expressions. So we're going back and just recapping some rules of exponents, but we're using actual numbers this time. So remember, 6 to the 12th times 6 to the 9th, when we multiply with the same base, just like if we were to do like x to the 12th and x to the 9th, we would add the exponents. So do the same thing here. We'll say 6 to the 21st. Now, could we actually evaluate and figure out what 6 to the 21st power is? Sure. But right now, we're just wanting to simplify those exponents. Next, on example 2, 3 to the 4th to the 12th. When you have an exponent raised to another exponent, you multiply them together. So it's 3 to the 48th. On number 3, you have an exponent outside of the parentheses with multiple terms inside of the exponents. So you do exponent times the exponent, and you get 2 to the 10th, 3 to the 12th. And then last but not least, not last but not least, but second to last, a negative exponent tells it to go to reciprocate. So if it's on the top, go to the bottom, bottom, go to the top. This is currently on the top of the invisible fraction. So we put it on the bottom, and it's 1 over 5 squared, which once again, yeah, we know what 5 squared is, but we're not being asked to do that right now. And then the last but not least one, number 5, 5 to the 7th, and 5 to the 3rd. When you have the same base being divided, you subtract exponents. So 7 minus 3, 5 to the 4th. All right, now we're going to use these same ones for rational ones, so ones that are fractions. So on example A, 5 to the 2/3 and 5 to the 1/2, we'd add these together. So you can't currently add these fractions by themselves. So you have to say, okay, let's get common denominators. Common denominator will be 6. So you multiply by 2 and 2 on the first one, and you get 5 to the 4 over 6. And the next one is going to be multiply by 3 and 3, and get 5 to the 3/6. Now, as we add those fractions, you get 5 to the 7 over 6. And that's as simplified as we need to make it right now. On letter B, we are multiplying these two. So 3/4 times 1 over 2, since this is an exponent to an exponent. And so we multiply top to the top, bottom to the bottom. So 3 times 1 is 3, 4 times 2 is 8. So x to the 3/8. Next, on letter C, we multiply this exponent to both exponents. So 4 times negative 1, or 5 times negative 1/5 is negative 1. And 5 times negative 1/5 again is negative 1. But now, since they're negative exponents, we'll reciprocate them and have 1 over 4 times 3. And since there's no more exponents, we are just going to go ahead and multiply them together and get 1 over 12. It's a little simpler than 5 to the 7/6 or x to the 3/8. Letter D, 7 over 7 to the 2/3. So we subtract these exponents, but remember, there's an invisible 1 on the 7 on the top. So really, that's 3 over 3 as well if we multiply the top and bottom by 3. So as we subtract that, you get 7 to the 1/3. Letter E. One way that might be helpful for us to look at this is say, okay, well, hey, multiply exponent to exponent and get 56 to the 5/4 over 7 to the 5/4. Now 56 and 7 are not the same base, so we can't just subtract those exponents. But what we can do is, since they're both to the same power or same exponent, we can say it's really like 56 over 7 and pretend that 5/4 hasn't been distributed yet. Because what would happen is we would have to multiply it back and you'd get exactly what you started with. Now, the reason this is helpful is because now we can just simplify 56 and 7 by dividing and get 8, which would then be to that 5/4 power. All right, so hey, do we remember that the nth root of a times b is really the same thing as the nth root of a times the nth root of b? Now, we haven't done that before with nth roots, but we did do it before with square roots. So we said, like, hey, the square root of 4 times 5 was really the square root of 4. Try that again. The square root of 4 times the square root of 5. And then the nth root of a over b, once again we did it with square roots, but the same principle applies, that it's the nth root of a over the nth root of b. And really, since these nth roots and radicals are really just exponents, but it would just be written as 1 over n, it's the same principle we just applied there on letter E, where we said, hey, it's like a over b to the 1 over n. And so you can either have it as a whole thing, or say it's a to the 1/nth and b to the 1/nth. It's really honestly the same thing we just did over here. It's just as exponents instead of radicals. Now we're going to use that, though, to help us simplify on these next couple. So on letter A, the 4th root of 27 and the 4th root of 3. So because they're both the same index number, they're both the same root, the 4th root, we can multiply the 3 and the 27 together, the insides, the radicands, if you will. So you end up getting the 4th root of 81. And conveniently for us, the 4th root of 81 is 3. Because 3 times 3 times 3 times 3 is 81. Same idea on letter B, but in reverse now. The 5th root of 96 and the 5th, they are the same root or index again. We can say, hey, it's one big one, and it's 96 over 3, the 5th root of 96 over 3. And so now we can take 96 divided by 3 and get 32. And so you have the 5th root of 32, which is, let me switch to orange here. Oh, I'm not doing Christmas colors. The 5th root of 32 is 2, and that would be your answer. Now, if you wanted to, and you notice, hey, these are the same index number, and you want to skip this blue step and essentially go straight to saying, hey, that's the 5th root of 32 by dividing those, you definitely can. All right, multiplying and dividing radicals, okay? So just like we were talking about there, you need a common index number, which is the number outside the radicand, that's a little small number that says, hey, this is this root. So on example 2a, we had the 4 as the index number, and in example 2b, we had the 5 as the index number. And we always combine the outsides with outsides, and you might guess it, the insides with insides. And that's the same thing we did with square roots, it's just we always had the same index of 2. So now on example 3, suggest maybe you try this on your own. So example 3a, same index of 3, so you multiply the outsides together, you get 2 times 6 is 12. The insides together, you get the 3rd root of 104. Now we can actually simplify that 3rd root of 104 though, just like we simplified square roots. So recall when we had a square root, let's say of, 16. So the square root of 16. Let me try a different one. That works too easily. Square root of 18. We might have said, hey, that's really the same thing as the square root of 9 times the square root of 2, and call it 3 square root 2. Well, we can do the same thing here with other roots like cube roots. So we can say 12, the cube root of 8, because 8 goes into 104, and 8 is a perfect cube. And the cube root of, 8 times 13 is 104. So the cube root of 8 and the cube root of 13 is the cube root of 104. Just like over here, the square root of 9 times the square root of 2 is the square root of 18. And that helps us because now we can say the cube root of 8 is 2. And we're just going to keep it as the cube root of 13 because nothing times itself 3 times is 13. Matter of fact, 13 is just a prime number. So now we say, hey, 12 times 2, 24 times the cube root of 13, and that would be our answer. So once again, really the same principles apply as when we did square roots previously. What is different now, though, is that we have to make sure the index numbers match, which they did. And we also have to say, okay, now we have to say, instead of the square root that goes into it, the perfect cube that goes into it, or so on and so forth, as far as different roots go. Example B. So, same thing works with dividing here, like we said. So because they have the same index or the same exponent, we can do 30 divided by negative 10, because those are not being raised to the power. Those are essentially the outsides here. Keep in mind this could be rewritten this way if you wanted. 30 times the fourth root of 32 over negative 10 times the fourth root of 2. And if you had it written that way, it might be a little easier to see that 30 and negative 10 are the outsides. So you get negative 3 there by dividing those. And the fourth root of 32 with the fourth root 2, divide 32 and 2, because they're the same exponent here. You end up getting the fourth root of 16, or 16 to the 1/4. Really, once again, the same thing. If you write it up here, it look like this. So if you prefer the radical model up in the green and blue, feel free to do that. If you prefer the exponent model in the orange, feel free to do that. So then we say, okay, the fourth root of 16, or 16 to the 1/4 power, which is once again the same thing, we get negative 3 times 2. So we multiply those together, we get negative 6 as our answer, either scenario. All right, now what happens when we add and subtract radicals? So just like before when we added and subtracted square roots, same principles, except for now, we're going to have other roots. So you need like radicals, so the same number underneath the radical, the same radicand, if you will, and you add the outsides. Not sure what happened there, but you add the outsides and keep the inside the same. Sort of like when you have 2x plus 3x, you call it 5x, but not 5x squared. So now, on example A, the cube root of 5 and the cube root of 40. Well, you might say, Mr. Castle, adding, and these aren't the same numbers, it's a 5 and a 40. And I'd say, yeah, you're right. Well, just like with square roots, what we did, we said, hey, the square root of 5 and the square root of maybe, 75, not 75, but let's go with 45. And we say, okay, the square root of 5 plus, well, the square root of 45 is really the square root of 9 times the square root of 5, which is really the square root of 5 plus 3 square root 5. Then we were able to say, okay, now it's 4 square root 5, because we do the invisible 1 plus the 3, the radicals are the same. And so similarly, we'll go through the same process here. We're saying, hey, the cube root of 5, well, let's see if a 5 goes into 40. And it does, and it's 5 times 8. And conveniently enough, the cube root of 8 we know is 2. So it's 2 times the cube root of 5. Now they are the same radical. So you take the imaginary 1, or the invisible 1, plus the 2, and get 3 times the cube root of 5. All right, on to example B. Same thing. This time, they're actually the same already. It's 8 to the 2/5 both times. So once again, if you wanted to write this as radicals, it'd be like this: 2 to the 5th root of 8 squared plus 10 and the 5th root of 8 squared. Either way, you'd end up having 12, 2 plus 10, and you'd have the 8 to the 2/5, or the 5th root of 8 squared. All right, moving on. Simplifying expressions involving variables. So, the cube root of y cubed. Well, a good way to think about this is saying, hey, what times itself 3 times is y cubed? You might say, well, we know that. Otherwise, if that's not making sense to you, maybe try rewriting these as fractions. Y to the 3 over 3, this number over the index. So we end up saying, oh, 3 over 3, that reduces to 1. So it's just y. And we can use that rule of thumb on all of these of taking the inside exponent divided by the index every time. And it's very similar to how we do division problems when we say it's like, oh, 12 divided by 4. You take the inside divided by the outside. So same idea. So on this, the next one to the right, y to the 12th and the cube root of that, we can really take 12 divided by 3 because rewritten, that's exactly what it would be. And you say, well, that's 4. So you get y to the 4th. The next one, we'd say, okay, well, 6 divided by 4, those can reduce just like they would reduce here. And we say, oh, that's 3 and 2. They can reduce here and say, hey, that's 3 and 2. And we say, okay, well, how many times does 2 go into 3? Well, 2 goes into 3 once, and there's a remainder, okay? So the remainder we are going to have to leave inside the root. And now you can write the little 2 there for the index since it's now a square root because we reduced it, or you can just leave it as an invisible. And so it'd be z times the square root of z. Same thing would apply here when there's multiple things. You take 10 divided by 5 and you get a squared, no remainder. And 18 divided by 5, which is, it goes into it 3 times completely with the remainder, so it'd be the 5th root of b to the 3rd because 3 was the remainder. And now on this one, we'd say, okay, well, 6 divided by 5, 5 goes into 6 once, and there's a remainder of 1, so the 5th root of d. So remember, when there is a remainder, the index number has to stay the same as it started, and you just put the remainder as the exponent inside. So 12 over 8, I would reduce that right away and say, hey, 4 goes into both, 2 and 3. And I would encourage you to try this one, the rest of it on your own. Well, 2 goes into 3 once, and there's a remainder of 1. And it's just a square root, so you don't have to write the 2 as the index. Go and try the last 2 on your own. 9 divided by 4, 2 with a remainder of 1. 9 divided by the invisible 2 would be a to the 4th, because you get 4 with 1 remainder. So now we can carry the same idea in as we simplify bigger expressions with stuff on the top and the bottom. We really do the same thing. 625, when you have normal numbers, it'd really be like saying, okay, well, what times what times what times what is 625? And you might not know that offhand. That's okay. Thankfully, we can use our handy dandy calculator for that if you want, with that nth root trick I was teaching you on the 7.1 video. So, a good way to think about it is one of 2 ways. Is really the same way, but doing individual things one at a time, the same way we're just doing them. And you can do that either in the problem or off to the side, and it's completely up to you. So if you want to do it into the problem, the problem itself, that's fine. If you want to do it off the side, that's fine. So maybe off to the side, we say, hey, the 4th root of 625, let's just deal with that number first. We say, oh, that's 5. Okay. And then the next thing, the 4th root of a to the 12th. Well, 12 divided by 4 is 3 with no remainder, so a cubed. And now the 4th root of c to the 5th. Well, 5 divided by 4 is 1 with a remainder of 1. So it ends up being c to the 4th root of, or c times the 4th root of c. And then the bottom is the 4th root of b to the 20th. And yeah, it's on the bottom, and we'll put it back on the bottom in a moment. But you can think of it as on the top for now, or if you want, you can put it on the bottom for now. Either way, it's really the same. And you can say, okay, well, 20 divided by 4 is 5 with no remainder. So since it started on the bottom, it has to stay on the bottom. And now we can take all those individual pieces and put them together in the problem. And just like they were doing before, all multiplying together except for the b to the fifth was on the bottom. So you have 5a cubed c, and then you have the fourth root of that one remainder c over b to the fifth. So the best way to approach these problems is just to take them piece by piece, deal with the number, and then deal with the variables one at a time. Next, letter B, 9x to the fifth minus x times the square root of x cubed. So just like on the previous examples where we're adding and subtracting radicals, you have to simplify these first using the methods we just learned. So 9x to the fifth, the square root of that, square root of 9 is 3. The square root of x to the fifth, 5 divided by 2, is x squared, with the remainder of that square root of x. Minus, well, 3 divided by the invisible 2 is 1. And so you add it to the pre-existent 1 out there, and you get x squared. Because remember, when you have the 1 out here, you really took 1 times this 3, which just became 3. So we had to take the x that came out when we did 3 divided by 2 and multiply it with this x, and when you multiply them, you add the exponents, because x times x is x squared. If that didn't make sense, try writing it out and say, hey, x, that x came out, and now you have the square root of x. So you say, hey, that's really x squared times the square root of x. And maybe that explanation made a little more sense to you. Now, since these are the same radicals, square root of x, we can combine these by taking 3x squared minus x squared. So that would be 2x squared times the square root of x. Letter C. I'd encourage you to take this on the same way we did letter A, where there's no numbers, no adding, subtracting, just division in this case. So one at a time, whether you write them out separately or not, p to the 8th and the 7th root of it. And remember, you also could, by the way, write it as the 7th root of p to the 8th and the 7th root of q to the 21st. So 8 divided by 7 is 1, with the remainder of 1. On the bottom, 21 divided by 7 is 3 with no remainder. And that's handy that there's no remainder, otherwise we would have had to rationalize, but we aren't learning that until next lesson. Now, let's move on to the next one, letter D. I would encourage you to try this one on your own. And actually, I should say before I had you start trying on your own, is you could write it as the radical version as well if you wanted. And it would be the same thing. And some of you might find that easier to write it as a radical version. The 1/5 power is really the same thing as the 5th root. Either way you think about it, if you take this way, you take the exponent to all the exponents. So 32 to the 1/5, m to the 1st, and n to the 6th. So that actually already simplified all of them except for 32 now, which is now to take the 5th root of 32, which is 2. Because 2 to the 5th power is 32. So you have 2m n to the 6th. And if you did what we did here in the orange, then you would just go through the same process we did on example A. Letter E, they're actually already identical radicals. That's super nice, the 4th root of p cubed. So we can just go ahead and subtract these. So 2/3 minus 5/3 is negative 3/3 times the 4th root of p to the 3rd. Now we might look at that and say, hey, wait a second, that's not quite simplified yet because negative 3 over 3 is the same thing as negative 1. So you have a negative 1 times the 4th root of p cubed, aka a negative 4th root of p cubed. If you write the 1 there, it's not wrong. All right, our last example of the day. I want to encourage you to try this one on your own. Use example E as a reference. All right, so if we look at these, if you were to look in this radical form, you might notice a little more straight away that it's 4a times the 6th root of b to the 5th minus 12a times the 6th root of b to the fifth. Those are the identical radicals, aka identical exponents. These are like terms, same variables, the same powers, so we can combine them. So we get negative 8 ab to the 5 6. Now, I will note real quick before ending the video is that if you are asked to give it in a certain notation, whether radicals or fractions, radicals or it might be called rational for the fractions, then make sure to give your answer in that notation. Otherwise, if it's not noted, you can give me the answer in either notation. So if you wanted to call that one in the rational or the fraction notation, you can, like we did, or you can give it in the radical notation, like this. And those are equivalent answers, just written differently. All right, that is all for section 7.2 today.